I'm going to use the pen so that we know. So if you remember, we start with our own PRF. Okay, so the PRF that we start is our y equals to, I'm using my notation, alpha plus beta x plus epsilon. And we had the assumption, and our assumption was epsilon is normally distributed with zero mean sigma square variance. Remember, I'm using no I here. This is I. There's no I under the sigma, which basically tells us that the model is not heteroscedastic. And our assumption previously was epsilon I and epsilon j is equal to 0, but now I am assuming that the model is not equal to 0. So we have three questions. So if we want to do the SRF, which we want to estimate the parameter, we are saying we are estimating y is equal to a plus bx plus e. So remember, that's what we are doing. We are estimating this. And if I use standard OLS, I will use b as a formula, summation of small x, small y divided by summation of small x square. So that's our standard formula for OLS estimation. Our question is, and this is our question, that number one question, obviously, why autocorrelation occurs. So what are the reasons for which we see autocorrelation? So remember, this is autocorrelation. So why this is there in a model, number one. The second question is, what happens to OLS estimation? Remember, we are doing OLS estimation. OLS estimation with autocorrelation. So if a model has correlation, what is the consequence? So in another way, we're saying, what are the consequences? And consequence may be nothing. If it is nothing, we are fine. We don't have to worry about it. So it's like you have a small spot on your face, cheek, black spot. Many people don't worry about it. Some people call it beauty spot. Means no consequence. Because it has no consequences, our answer is do nothing. But if it has consequences, we need to do two things. One, how to detect. So remember, the logic should be clear in our mind. Sorry, where is my eraser? How to detect. And once I detect it, next question is how to remove. Because if I find a disease, we need to remove it. So these are the questions that we want to solve. Okay, so that's technically, we have 2A and we have 2B. Excuse me. So remember that what we're looking at, these are the fundamental questions we are trying to solve. On the question of autocorrelation, why it occurs, that's the question that if we want to deal with it, answer is very simple. We go down and we have 12.1. So remember, 12.1 is a section which says nature of the problem, why the problem occurs. That's the 12.1 sections. Okay, so remember, let me remove the, okay, so remove the drawing. So, okay, so First logic is, remember, this is autocorrelation. So remember the logic of the autocorrelation. We are saying that autocorrelation means, change the color. No, so autocorrelation means this. This is autocorrelation. Means if I have observation I, which is the first observation, and if I j, which is the second observation, and if you remember my model, y is equal to alpha plus beta x plus epsilon. So if I have first observation, I have y1 equal to alpha plus beta x1 plus epsilon 1. Then I have y2, which is my second observation, which is alpha plus beta x2 plus epsilon 2. We're saying these two errors are correlated. In other words, this error is linked to this. So think about it. Is it true? So if let's say that, so think about a logic. If there is this observation, building number 1, and there is a building number 2, two observation, I'm looking at it. Question is, are these two building 1 and building 2? Remember, I'm collecting data from building 1, I'm collecting data from building 2, so I've collected two data. So the question is, remember we're explaining why. Why could be any behavioral variable. Remember, economists are talking with, we are looking at behavioral variable. So these are a behavioral variable. It could be income, it could be whatever it is. So if you look into economics, demand, it could be supply, it could be employment. So the question is, if a person is employed here, do you think this person's employment status is linked to this person's employment status or not? So you are unemployed. So you think, does it mean that my neighbor should be also unemployed? Is it correlated at all? What do you think? Anyone?
Not correlated.
Not correlated. Okay, so I'm going to watch some students anyway. Let me open up my screen. Okay. So I want all of the people to respond, and whenever you are talking, unmute yourself and talk. Okay, that's my objective. So class should be just like you are in the class. Okay, so that's the feeling should be. Even though it's an online, unlike many other online classes, my online classes has a lot of interaction. Okay, so be prepared with your microphone and talk and participate.
Sir,
So,
it could very well be correlated. Like, suppose the economy is in downturn, so a lot of people are unemployed.
no, but see, my unemployment, is it linked to my neighbor's unemployment? For example, my behavior, I'm purchasing today basmati rice. Do you think my neighbor is going to purchase basmati rice?
No, sir. Different.
No. So remember, there is a lot of behavior when my behavior is not linked to my neighbor's behavior. That's number one, the possibility. Number two, think about over time. So I'm talking about our individuals. I'm talking about, if I'm talking about our individuals, possible that two observations, two individuals, my behavior and my neighbor's behavior may not be same. I'm using the word may. Be careful on that idea, which I'm not saying it cannot. So it's possible that sometimes it may not be. So coming back on this logic, I'm just thinking about the logic of it. Coming back on this logic, what I'm saying, that let's look at over time. Over time, your behavior, not over individual. So what I'm saying, look at the budget of the government of Bangladesh. I'm just giving an example. So we have a budget deficit in 2025. What do you think? In 2026, budget will be also deficit or surplus?
Deficits.
Anyone?
Deficit.
Deficit. Why? Any reason for
আর
your
এত আর্লি সেই ডেফিসিটটা রিকভার করা তো প্রবলি পসিবল হবে না যে 2026 আবার সারপ্লাসে যাবে, সো ইট রিকোয়ার্স টাইম।
Okay, so you are thinking that the behavior is not going to change over time. Think about consumption behavior another way. This year, for example, we are spending in the whole Bangladesh 25 consumption expenditure. I'm giving an example. Let's say it is $350 billion. That's much I have spent in 2025. What do you think? 2026, it will be less than this or more than this?
More than this.
Probably more than this.
More than this. So you think about 275, just an example. But what I'm trying to tell you that sometimes these are very correlated. Your behavior today and your behavior tomorrow are correlated. So yes, you will find out that there is a possibility that when I'm dealing with data, the data over time, or it could be over individual. I'm giving another example, which is a probably better example. You studied fire at, let's say, in a building. There is a fire in this building. What is the probability of this building will also be catching fire?
Probability is high.
So remember, sometimes it's correlated. Or think another way. If this is a neighborhood. So if I'm living in neighborhood and I'm looking at a richer neighborhood, do you think my neighbor is also probably rich? Similar people live in the similar area. So there is also a possibility of correlation between two observations, because I just take my first sample, who is a rich person. My second sample, it may also be a richer person, because I'm actually doing a survey in Gulshan area, for example. So in other words, there are also correlation between two individuals, as well as it is also possible that there is a correlation between two over time. And that's exactly what I'm saying, that there may be link between observation 1 and observation 2, but it could be also linked between observation 1 and observation 3. Take another example, which is that if I buy a stock today, which is day 1, I'm going to sell it in day 4. Before that, I need to hold it for 3 days. So there is a rule. So my purchase, whatever I bought in day 1, I'm selling in day 4. So these two events are correlated, because that's where the demand was and that's where the supply. So there is a correlation over time, and it may not be 1 and 2 correlation, it may be 1 and 4 correlation. So that's why we have correlation not only, and this is known as order of correlation. We're creating order of autocorrelation. So if you say that autocorrelation exists, we say, well, unfortunately or fortunately, there is an order. And order is, if it is 1 and 2, between these two, we say first order. If it is 1 and 3, remember, we say second order. Difference between them. If it is 1 and 4, we're saying it is third order. In other words, difference between them creates the order of correlation. So we're saying, look, observation 1 and observation 4 are connected to each other. So depending on your data, there may be some kind of correlation may exist in our data, and that is perfectly, not unexpected. That's what I'm trying to say. That is not unexpected for a data set. Okay. So coming back on this one, so this is why we're saying that it's like they're saying quarterly data. Take an example. They say, look, if you're looking at quarterly data, if there is a first quarter bad weather, second quarter will be linked to it sometimes. So economy is linked over time. So what we assumed initially, our assumption was expectation of epsilon 1 and epsilon I and epsilon j is 0 for all I not equal to j. So if I and j are not same, we assume this to be equal to 0, which says this is the assumption of non-autocorrelation. So we assume that model has to be not autocorrelation, but in real life, we are saying there are many data which are correlated. So that is where the first logic should be clear in our mind, that, okay, there are data where the data is correlated and it sometimes happen. And so what are the reasons for these happenings? one of the reasons for happening like this, if you go down in the book, they will say inertia. The first reason is called inertia. So you see, I'm not going to read this out, but I want you to read it. One of the reasons is inertia, which means what happens yesterday is probably follow tomorrow. There's a link between my behavior today and my behavior tomorrow. There's a link between what I have eaten today and what I will eat tomorrow. They're highly correlated. So inertia is probably one of the reasons why you will find out a lot of macroeconomic data, time series data. Remember this. Some suffers from inertia, and that's very common in economic model. So that's number one, that if you want to think about it, what are the reasons? We said, okay, inertia is one of the reasons for autocorrelation. So let's now go to the second reason. And what does it mean when it's autocorrelation? It actually means very simple. So if you look into this data, this diagram is pretty good. This diagram tells you that, look, this is your, according to my notation, U means epsilon and U hat means E. So remember, my notation and textbook notations are not same. So this is epsilon and this is E. So if you remember my model, Y equal to alpha plus beta X plus epsilon, Y equal to A plus BX plus E. So remember, this is my PRF. I'm writing this every time deliberately to show you that anytime you run an econometric model, you talk about it in your answer script, you should always write this too, so that we know the notation. Okay, so this is my notation. And what we're saying, this is time. So we're saying, look at this one. This error, this is E. If I look at E, this E is linked to the over time. This is a pattern. So this is autocorrelated. So yes, the model is autocorrelated because I can see the errors are pattern-wise linked. This is also true, autocorrelated. This is also true, autocorrelated. This is also true, autocorrelated. So you see, autocorrelation can be observed right from your data, that we can see autocorrelation. Okay, so if I now go down and say, okay, how about this one, the last one? Let me erase this. I'm keeping my equation, PRF, SRF, but I'm erasing. So if you look into this one, you realize that there is no pattern. So this is non-autocorrelated. So you realize that you see the non-autocorrelated versus correlated data based on a simple logic, which is if you plot E on T or I. T means if it is a time series data, or I means it's an individual cross-section. So this is a time series data, and this is a cross-section data, depending on the data set you are talking about. So if you have a cross-section data, if you observe, if you look into the error terms, EI on I, and if it's a time series data, if you do it ET on T, then you find out that, yes, I can see the autocorrelation. But remember, this is how do you observe autocorrelation, not the causes of autocorrelation. Causes of autocorrelation we have just discussed. So let me go down and say, okay, what are the other reasons? There is a second reason. It's difficult to observe right now, which is called specification bias. So we have a full chapter on specification bias. Probably tomorrow we'll talk about it. I'm trying to rethink about it, how to show you that these chapters. So let me give you a home task at this point, which is you go to my website, YouTube site. So remember, I'm showing you my YouTube site. And there is a lecture on specification error. Again, this is 3 years ago. You can feel that, which is COVID. So this is a lecture during COVID, and I have spoken about specification error. I want you to listen to it. This is about 1 hour lecture. Okay. And that's in the next class, we will discuss if there is a problem. And there is a lecture on multi-coordinate. So these are the 2 lectures I want to give you as home task. Okay, so this is about 42 minutes and this is about an hour. So tonight when you go home, when you are at home, you will be, there is a lot of lectures just to show you what. So this is a lecture on specification error. It reviews exactly Gujarati's chapter on specification error. This is a lecture on multicollinearity, which is Gujarati chapter 10. So you can exactly read it. You can listen to it. And if you have the Gujarati book in front of you, you can exactly follow. This is just like my lecture right now. There are quite a lot of other things, and these are probably quite good for other purposes. Okay, so I have review of econometric model, mostly for higher level econometrics and other issues. And these are all modeling issues for those who are working on thesis. But I think these 2 lectures, you should be able to listen to it. So tomorrow it will be more of a review based that I'm assuming that you have listened to both of these lectures. So remember, that is my assumption. So let me go back to my class. Where is my class? This is my next logic. Okay, here. So specification. So the reason I'm saying that it's very difficult to explain specification at the moment, but tomorrow you'll be clear on this. So there are specification bias. So it basically means this. I am assuming y equal to alpha plus beta x plus epsilon. What it means that if I look into my x here and y here, like this. Okay. So if I'm looking at x versus y, and if I have looked at my data like this, just an example. So what you see, if you run a model, the model will look like this. This is this model. But if you look into the data, the model should have been like this. So the equation PRF that I started with was wrong. Means I started with the wrong assumption. That's called bias. I have a bias. I thought it is a linear model. But in fact, this should have been the model. The model should have been alpha plus beta x plus gamma x square plus epsilon. So if I had run this second model, it would have been a nice one. But remember what I did. I started with a linear model. And that is known as specification bias. What I have done, that there is a variable called x square. Remember? And I have excluded that. I did not include in my model. The model should have been y equal to alpha plus beta x plus gamma x square plus epsilon. So this variable I have excluded. It could be x square, quadratic variable. It could be another variable. What is another variable? I thought quantity demand is a function of price, but I forgot income. So income could be creating all this problem. So I'm giving you the logic that if you run a model, all these are possible scenarios. So specification bias often create a kind of a autocorrelation in my model that looks like an autocorrelation, but it's not autocorrelation. It's because there is a specification bias. So that's what it is. So they have explained this, which is this. What is basically saying, if you think about the way I was explaining it, just to give you an idea, that I was looking at this data set. So this is my data set. And I was using a linear line. Remember, this is my y, which means if I now plot error terms, what you see here, the error is negative. Here, the error is positive. Here, the error is negative. So you will find out negative, positive, and negative errors. So your error will look like this. So if I have time here and E here, it will look like this, which is basically they're saying, look, I can see that the model is autocorrelated, but it's not autocorrelated, it's misspecification. I did not specify the model properly. Okay, so that's the other reasons for So specification, this is the other one they're saying. Specification bias can be talked about as incorrect functional form, as I said, out x square. So I am using both of them. I give you the idea that y equal to alpha plus beta x plus gamma x square plus epsilon. And this is exactly what it is. Another way to y equal to alpha plus beta x plus gamma z, which is income, plus epsilon. So that's a missing variable, and that's a wrong functional form. It's supposed to be quadratic, but we did not use the quadratic model. So there are different reasons why you see specification error enters into correlation or autocorrelation. You see autocorrelation in the model and you think, oh, I see a problem. It's like fever. That symptom appears. Autocorrelation symptom appears, but it's maybe for different reasons. So there are all these reasons for looking at it. The cobweb phenomena. Anyone idea about cobweb phenomena? What is cobweb phenomena? It's most coming from the agriculture economy. How many of you have done agriculture economics? Anyone did agri economics course?
Yes, sir.
Parija?
Yes, sir.
Okay. Did you talk about cobweb phenomena?
Yes, curve looking like spiral going in and going out.
The idea is very simple, that what you see, if you look into the time, if this year have a bumper production, the price will be low. Next year, because the price is low, people will not produce, so the price will be high. So this phenomena means if you look into the price over time, you'll find out 1 year low, next time high. And because next time high, next year people will produce again, so price will be low. So the price will follow this phenomenon. This is known as a cobweb phenomena, which means your behavior is linked from 1 year to the next year, which is also known as the autocorrelation. So autocorrelation is there because there's a cobweb phenomena in the system. You cannot, it's often very clear. That's what happened. Anytime there's a crisis in the economy, agriculture, people say, oh, next year I will do this. And next year when everyone does it, price drops. So that's why this kind of phenomena appears in many of the cases. So that's another reason for autocorrelation in our model. So lag phenomena is the other one, which means my behavior today is dependent on my behavior yesterday, my indebtedness. So in other words, remember Bangladesh has a large amount of foreign debt, for example, just to give an example. So my debt today is linked to my debt yesterday. Okay, so that's called lag phenomena, means my behavior is linked with my past. And if that happens, you will find out the model will show autocorrelation. Okay. Sometimes manipulation of data. This is what happens. We interpolate the data. What does it mean? We start looking in the data. For example, this happens a lot in macroeconomics, that we have the data here, one data set here, 1986, just an example. Another data here, 1991. Another data here, 2001. So now we said, what do I do? So we said, oh, that's actually, we can create I said, okay, this data must be like this. So we start interpolating data in the middle, which was missing data. Because a lot of time we have missing data in the data set. And if you have a missing data, what to do with it? So we say, oh, I can see the trend. So this is my original data. This is my original data. This is my original. But between this, I created a trend which I have manipulated it. Remember, manipulation is not a bad word. We're saying we have extrapolated. But if we do this, we can actually create a kind of an autocorrelation in the model. So that's another reason why autocorrelation appears in a model. Another reason that I last one, the data transformation, which is also very similar, that I have changed the data, whatever way you do it. Okay. So coming back to the logic that we now see, there are good reasons for us to believe that there is autocorrelation in the model. So now the starting logic is, Next logic is, how do I detect? Because the data, remember the problem of the data cannot tell you I'm suffering from fever. Data cannot tell you I'm suffering from autocorrelation. So the question is how to, first of all, let's go backward. First of all, that if there is an autocorrelation, we realize that autocorrelation is there. What are the consequences? Okay, what happens to my estimation? Because I'm going to use OLS. So we want to know the consequences. And remember, what is our OLS model should be blue. That's what we want. We want unbiased, two characteristics. There's technically three, but mostly we talk about two. First characteristics is it has to be unbiased. Means if I run OLS, the model should be unbiased. Second, it has to be efficient. Efficient means the model, remember the wording is important. Efficient means the model is the variance of the estimator, or variance of B must be minimal. And this means expectation of B must be equal to beta. So remember these are, and third one is called consistency, which we don't talk much, but I think conceptually we should know. Estimator must be consistent. What does it mean? It means the expectation of B equal to beta, and this should be true if I limit it with n goes to infinity. It means as I increase the sample size, it should be consistent. If I increase the sample size and the parameter estimation jumps from positive to negative, from low value to very high value, that means it's not, you don't trust it. So this is almost like a large sample versus. So these are the three things that we do. Most of the time we talk about these two. Okay, so I'm just giving you the logic that what are the consequence means this must be there. For a fever, doctors is, because we said, oh, what is, how do I know nothing happens? Answer is, well, don't worry about it. A black spot on my face is not a problem. People don't look at it as a bad sign. That's an example. I don't feel bad, which is I don't have a fever. So there are consequences. I'm still normal. As long as I can behave normally, many of the diseases we ignore. But if you cannot behave normally, that's a problem. That's when we said, oh, we need to see the doctor. So let's now start with a assumption. So let's now start with a model, which is y equals to alpha plus beta x plus epsilon. Remember, our epsilon is normally distributed with zero mean and sigma square variance. Let's think about this model as a what you call autocorrelated model, which we're saying that epsilon t is linked with rho. Remember how to write rho. I'm writing it again so that you know how to write it. So rho, don't go like a p. It's the other way around. Go like this. This is rho. So remember the writing standard of rho is like this. Epsilon t minus 1 plus, let's say, nu t. What we're saying that this is the error today. This is the error yesterday. So this is today. I'm just giving an example. And this is yesterday. What we're saying, my behavior today is linked. And as long as rho is not equal to 0, if it is equal to 0, that means my behavior today is not linked to yesterday. But if it is not equal to 0, remember, that basically means this model is autocorrelated, and this is known as first order autocorrelation. Why first order? Because the difference between the two is 1. So this is first order. I'm assuming a model of first order autocorrelation, and I want to see if the model is autocorrelated of first order, what is the consequence? That's our question that we are now dealing with. Okay, so let me go down. So that's exactly what they have done. Okay, so that's our standard one. So let me see what they have done. So if we do this, let me look into this. I don't think I can see it here. Don't worry about it. I have done a few other things, which will come back later. You see where they have done it. Does not look like they have done it here. Okay, don't worry. Let me go to a space where we were doing it. Okay, so let's now do this one. So we said, okay, we have this model. And if I run my SRF, remember this is my PRF. If I have SRF, my SRF is y equal to a plus, a plus bx plus e. So I said, look, b by definition is summation of small x, small y divided by summation of small x squared, which is equivalent of summation of small x, big Y, divided by summation of small x squared, which is equivalent of summation of small x, and this is alpha plus beta x, remember beta big X, plus epsilon divided by summation of small x squared. Remember what I'm doing? I'm basically saying, okay, I can look into this one. And if I look into this one, just a second, how do I do it? Okay, let's try it on this page. I don't want to. Okay, so come here. And now I'm saying if I expand this further, it will be alpha into summation of small x divided by summation of x squared plus beta into summation of small x big X divided by summation of x plus summation of small x epsilon divided by summation of x squared, which is equal to b is equal to, this would be 0. Okay, so remember summation of small x by definition is equal to 0. Okay, just a second. I need to put power. Okay. Okay. So we have this is equal to 0. So there is nothing there. And we also know summation of small x big X equal to summation of small x squared. Remember, we have done all of them. So I'm not repeating this. So this will be equivalent of beta plus summation of small x epsilon divided by summation of x squared. Now, if I run an expectation here, I should be running an expectation here. And if I run an expectation here, beta is a constant, so it will be beta, and it will be summation of expectation of x epsilon divided by summation of x squared, which is equal to 0. Why? Because we know the covariance. Remember, we know the covariance of x and epsilon is equal to 0. Remember, we changed this assumption. What is the assumption we changed? Expectation of epsilon I, epsilon j is not equal to 0. But our other assumption, which is covariance of x and epsilon equal to 0, still there, which means expectation of b is equal to beta, which means it is still unbiased. So we now realize that, we don't have a big problem. It is still unbiased. Am I clear? No? Anyone?
Yes, sir.
Okay. So what I'm saying, that first logic is, remember we are looking for 3 logic. First logic is, it is still unbiased. So I run a regression model which has autocorrelation. We say, well, don't worry, the model is still unbiased. Is it efficient? That's our next logical question. Is it efficient? How do I answer it? So in order to answer the efficiency, let me erase this part. So I'm erasing this part. Keeping some part. Just a second. So remember, this is my model. If it is, so the next logical question, it is variance. That's exactly what the variance is they're looking at. So what they have done, they said, look, if I do the variance with auto, they said the model is auto-regressive of order 1, AR1. Remember what is AR1? AR1 means auto-regressive, which is autocorrelation. Auto-regressive of order 1. And that's exactly what we are assuming. So this model is AR1 model. So remember, this is AR1 model. So what they're saying, if I have a variance, the variance formula will be looking like this. So this I want as a home task. What you will find out when you look into the variance, remember variance of BAR1. BAR1 means the model is autoregressive. This will be equivalent of expectation of BAR1 minus, remember this is what we still unbiased, so I can still say AR1 and BAR1 is exactly same because they are unbiased, minus beta, which is unbiased formula, whole square. And if you run this, remember, if you run this, these terms will appear. So they're saying these terms will appear. And now the question of this one comes. So let me prove what does it mean. So we said our model epsilon t is equal to rho epsilon t minus 1 plus nu t, which is another error term. But this error term is not autocorrelated. Okay? So think about this one. So if I now say that multiply this with epsilon t minus 1, epsilon t, this will be equivalent of rho epsilon t minus 1 whole square plus epsilon t minus 1 into nu t. So think about it as this. We can do the another way. We can say epsilon t minus 1 is equal to rho epsilon t minus 2 plus nu t minus 1. So if you do this expansion, so in other words, if I replace this one with this one, so remember this one with this one. So if you look into this way, what you will find out, so think about this, let me look at the proof. Proof is right there. Just a second. The proof is there. That should go up. That's the one I was skipping. Right here. So they said that what you will find out is this one. That if you look at t plus 1 or minus 1 doesn't matter. Remember this one. You'll find out it is rho to the power s this. And this, so remember this is in C in appendix 12.A. So let's go to the appendix 12.A. Where is 12.A? Just a second. 12.A should be before this one. Okay, so 12.A. So I want you to look into this proof. This is a proof here. So that's exactly the proof. So this is the proof. So they're saying if you have an under AR1, this is my model. Remember, U t is my notation is epsilon t. U t minus 1, my notation is epsilon t minus 1. Same thing, doesn't matter. So they said, look, if you have this, if you run an expectation, this will be like this. Okay? And if you look into this one, if you t is rho this, so t minus 1 will be rho square. And that way, and remember multiplication. So this will be, so in other words, what we're saying in a different way is like this. Let me do it easily. It's difficult than this. So let me do it easily. We said epsilon t is equal to rho epsilon t minus 1 plus nu t. So if I say variance of epsilon t, by definition is the variance of rho epsilon t minus 1 plus nu t. Remember the logic. Variance of this side must be the equivalent of the variance of the other side, which is equivalent of variance of rho epsilon t minus 1 plus variance of nu t plus 2 covariance of nu t, sorry, nu t and rho t minus 1. So the logic is that there are two terms, a plus b. So it's a square plus b square plus 2ab. That's the whole logic. This one would be, because this is a constant, so rho will come out as a square. And this will be variance of epsilon t minus 1. Plus this will be sigma square nu t, which is another variance. And we're assuming these two are uncorrelated. It's not, because of this, we see the rest is 0. So what I have now on the left-hand side, this is sigma square epsilon. So we have sigma square epsilon is equal to, remember, this is same V. So this will be rho square sigma square epsilon plus sigma square nu plus sigma square nu. So remember that. So if I look into this one, just to go down, so this will be sigma square nu, which basically means if I want to know the logic of it, is said, look, if I come back here, it will be 1 minus rho square sigma square nu equal to sigma square p. So if you look into this one, this will be equivalent of sigma square epsilon is equal to sigma square nu divided by 1 minus rho square, 1 minus rho square. That's exactly this. Okay, so remember there is a notational problem, that's why it looks different. And this is the variance of the epsilon. So remember, because of autocorrelation, the variance becomes this. So this is the new variance that we have in the model. Okay, so that's exactly the proof the book has provided. So go back to the chapter again. See the chapter. Come back here. This is the chapter. And we are now saying that if we run the model, we have the variance also. Okay. And what basically we're saying that unfortunately the variance, now remember what I now know, the variance, if you look into the variance, original variance, if I look at the variance of B with OLS, it is sigma square divided by summation of x square. And now we realize it is no longer equivalent of this. And since this is the most efficient, so we're saying a variance of B with AR1 model is bigger than the variance of B with OLS model. Remember the standard my model. So which basically means we have a problem. What is the problem? Our problem is variance of B, remember the one, if the model is suffering from autocorrelation, becomes large. So that's our first logic, is that the variance becomes large. So coming back, we now realize that the variance under OLS, just like what we did in heteroscedasticity, it is also large. And if it is large, which means if I look at the variance, remember that if we look at the variance of B under autocorrelation, which is larger than variance of B under standard circumstances, that means basically means T value becomes small. Remember the same problem that we have discussed. What does it mean? It means if I'm looking at a distribution of B, remember that's what we're looking at. And if I'm looking at this is my beta. Remember, I'm looking for beta. So this is my 95% confidence level within beta. T becomes small means T value may come back to here. And this is my null hypothesis. Null hypothesis is beta equal to 0. Beta equal to 0 means, in my model, y equal to alpha plus beta x plus epsilon. And if beta equal to 0, that basically means y is equal to alpha plus epsilon, because this is 0, which means this model is not a function of x, because in this model x does not exist. And our assumption was, we collected the data of x because we thought y is a function of x. That was our model. So we are concluding that y is not connected to, linearly connected to x, not connected, linearly not connected to x, because my t value has become here. And why the t value has come here? T value has come here because t means b by s of b, and s of b has become large, which means this t has come here, which means t is giving me a wrong signal because of the inefficient estimate of the variance. So remember the logic, that because of the high variance of b, just like heteroscedasticity, we end up not rejecting the null hypothesis. Not rejecting the null hypothesis basically means we're saying beta is equal to 0, which we're saying that y is not at all connected to x. But remember that y was connected to it. That's why we ran the regression. Our theory was y is a function of x. Based on this theory, we said y equal to alpha plus beta x plus epsilon. And now we're saying that is not. Now it may be that this is true, but it may also be this has happened because of the larger variance. And that's exactly what we're saying, that we end up rejecting the, not rejecting the wrong null hypothesis. And if we cannot reject the null hypothesis, we end up concluding that y is not connected to x. So that's exactly the idea. Okay, so that's exactly the idea. So we said we have a problem in this particular model. So which basically means, so remember that, which this is what, we'll come back to GLS later on. GLS will reduce the variance. That's what it is. We'll come back to this one later, how to solve it. Okay, so end of the day, what we're saying, if we go back, that our variance becomes large. Remember, that's what exactly what they're saying. Remember, as I said, variance of beta 2 is smaller than the variance of beta 2 with AR1, with autocorrelation 1. If that is the case, we have a problem in the model. So that's the first problem that we realized, that, okay, autocorrelation is a problem. Okay, now the question is, if autocorrelation is a problem, what do I do? How do I detect it? Because the data cannot talk to me. So if the data cannot talk to me, how do I detect it? Obviously, the first method of detection is graphical method. I have already explained it. What do I explain it? I run my OLS. What is OLS? Y on X, regress. That's basically OLS. Regress Y on X. That's my first choice. If I regress my first choice, I could run this and find E. Remember, I can always find E. What is E? E is equal to Y minus Y hat. So we can find it. And then we plot E on observation. And if we E on observation, if we do this, that basically means, and if the pattern, remember this is my observation, and if the pattern is like this, oh, I can see autocorrelation. So graphically, we can see autocorrelation in the model, just like we would see the same thing in heteroscedasticity. So that's the first method of testing autocorrelation. However, there is a problem. What is the problem? Problem is it's only on the data. And I'm not interested in the data. What I'm interested is in the population. So that's why we need to have test test something. And that's exactly what the second method came. The second method is known as runs test. Not a very good test. Nowadays, people don't use it. But this was done when there was no computer. So, and the idea was when I look into error terms, remember the error terms? So this is the idea. So remember, I'm giving you the logic. This is the idea of, if I plot T and if I plot E, what we see that here error terms are negative. Within here, the error terms are positive. After this is negative. That's exactly. So this is what they say. Negative, positive, negative. We see a pattern. It's supposed to be, if you look into carefully, if there's no autocorrelation, it should be negative, positive, negative, positive, negative, positive, negative, something like this. But now we see a pattern, a range within which it is all positive, a range when it is negative, another range which is negative. And that means the model has autocorrelation. So how do I test it? How do I know it is also in the population? That's the logic. So in order to know this, they said, okay, if I have this, let us define certain things. What is the define certain things? So let us define number one, N1. What is N1? Number of positive symbol. How many positive signs? Remember, let's say there are 20 data. So we have N1 equal to 20 in this range. Let's say this is here 10 and this is here 5. So N1 is 10, 20. N2 is 10 plus 5, which is 15. And what is N? Total observation? Total observation is 35. So they say, remember, total observation is this. N1 is positive. N2 is negative. So a number of runs. How many runs? 1, 2, 3 runs. In other words, it changes the sequence of positive to negative 3 times. So then they say the run itself can be tested, whether it's significant or not, because if it is too many runs, that's probably what we are looking for, because you want positive, negative, negative, positive, positive, negative, something like this. But you are seeing a small, so this is one. So they said we have a non-parametric distribution. What is the distribution? The distribution is, again, this is just a second. So this is the distribution, and the distribution is R, which is what I'm looking for. R has an expected value of this, and variance of R is this. So again, these are Department of Statistics, they have solved it. It's a non-parametric statistics. And they said, based on this, I can actually do the test. What is doing the test? Very simple. So they have given an example. I want you to follow this example. So follow this example. What is the example? They said we have done a case, and this is what they have done. N1 is, remember, we know that number of minuses is 19, and 2 is number of pluses, which is 21, R equal to 3, remember the example. So they said in that case, using those formula, I find out expectation R of this and variance R of this, and standard error is this. So based on this, they have a confidence interval. So they said, based on this, I have a confidence interval. And based on the interval, I can do the test. So if you go to the appendix D, this is the new critical table. So remember appendix, there is a critical table, but don't worry about it. I'm not going to ask you to do this. But I just want you to make sure that we understand the logic. So it is there. In the run test. So this is one test. Don't use it nowadays. But the more important test is Darwin-Watson test. So this is the most computer-oriented. And nowadays, computer does Darwin-Watson test automatically. But what is Darwin-Watson test? So Darwin-Watson was very smart. He is a very smart person. He started with the logic of, let me go back to, so this one. So he said, what is autocorrelation? Autocorrelation is epsilon t is equal to rho epsilon t minus 1 plus nu t. Remember, this is the first order autocorrelation. So he said, imagine I am estimating this. If I'm estimating this, I will be estimating E t equal to rho hat E t minus 1 plus, let's say, nu hat t. So this is something like this. What is the rho hat formula? Rho hat formula will be summation of et minus 1 divided by summation of et minus 1 whole square. Imagine this is your y and this is your x and this is your b. So remember, this is like this model. Remember this model. If I have this model, my b formula is summation of small xy divided by summation of small x square. That's exactly what I have done. So he said, imagine this is my d. So he said, okay, so this is, sorry, not this is d. So this is the logic. So his idea was that I can define d. So he created his own d. And he said it is equivalent of, in my notation, summation of et minus et minus 1 whole square divided by summation of et square. So remember, this is his logic. He said, this is my d. And he suggested that if you use this d, remember this is my d, if you use this d, I would be able to test whether there is an autocorrelation or not. And for that, the logic is very simple. So that's exactly what I've done. So if I now go back to this formula, remember this square, if you expand this, you will get this. So remember the formula they are expanding, you will get this formula. So a square plus b square minus 2ab. Remember, his d was, let me write it down, summation of et minus et minus 1 whole square divided by summation of et square. That was his formula. So he said, look, I'm just expanding it, a minus b whole square. So created this. If you now do this, then you find out very interesting thing. So first one, if you now look into this, expand this one. So this will be, if you logically look into this one, these two will be approximately same. What they are saying, this is summation of e t square and summation of e t minus 1 square. They are very much close to each other because there is only one observation missing. Other observations are all same and errors are small numbers. So they're saying they are most same, which means this two I can write as 2 summation of et square. So if I have 2 summation of et square, so I can rewrite this one. I said, look, instead of this one, I said this and this 2. So I can take this 2 common. And if I take this 2 common, and this is et square divided by et square, so they cancel each other, becomes 1. And this 2 is there, so this is what it is. So he says my d is equivalent of this. So that's his definition of d. So his d is equivalence of, remember, this is rho hat. So his d is equivalent of 2, 1 minus rho hat. So remember my rho hat, why I was doing it here. So it says this d is equivalent of 2 minus rho hat. So in other words, if rho hat is equal to, so now he said, oh, now look at this carefully. What does it mean? If rho hat equal to 0, d is equal to, how much is the value of d? If this is equal to 0? 2. So d value 2 means there is no autocorrelation. And if rho is equal to plus 1 means positive autocorrelation. So if rho hat equal to plus 1, then d becomes 0. And if rho is equal to minus 1, which is negative autocorrelation, then this becomes 4. So he said my d value is less than 4, bigger than 0. If it is 2, the model has no autocorrelation. So I said, all we have to do test d. So he realized he's very cleverly created a test value. And he said, do this. Okay. So based on this, he said, okay, that's basically I can rerun this model and I can test d. That's the Darwin-Watson test. Nowadays, and that's exactly what he's doing here. But he has done a lot of mathematical simulation, and he found out that there is a problem in this region.
Darwin.
And this is the region of indecision. He said, sometimes I can find data value here. Sometimes it shows positive, sometimes it shows negative correlation. Sometimes no correlation, sometimes correlation. So he said, I have the DL and DU. So he created a range of values, and he said, within these values, I don't know whether it's a positive or negative autocorrelation. But if it is between these two values, there is no autocorrelation. But if it is here, there is a negative autocorrelation. If it is here, there is a positive correlation. And within this range, he said, I'm not sure. So he said, why don't you just do this testing? Very simple, on your data. So nowadays, it's actually all software does. So in Stata, it does automatically. Again, remember the home task. This is also home task. Mahbub is here. No?
Hello, sir, শুনতে পাচ্ছেন
Sir,
আমাকে?
Mohammed is not here right now.
Hello.
আছে শোনা যাচ্ছে। ওকে,
জি স্যার, আমি জয়েন করেছি স্যার কিছুক্ষণ আগে। জি স্যার।
ইয়ে কে আমাদের টিএ জন্য নাম ভুলে গেছে, ওর নাম তো ভুলে যায়।
রাইন আপু স্যার।
লাইনে আছে?
Sir,
sir.
I'm here, sir, I'm here.
ওকে, গুড, রাইট। ওকে, তো তুমি ওই নোট রাখো, এই যে টেস্টগুলো ডারবিন-ওয়াটসন টেস্টটা করতে হবে তাদের ডাটা থেকে।
Yes, sir, Darwin-Watson for the assignment, right?
Yeah, so the idea is very simple. See, that's exactly what I'm doing. They said, okay, so you have these, and this is so zero. I have already shown all of them. So basically, what we're saying, we can do the test, and this is how it works. They say run OLS. So remember the test. They have already given you the idea. 4 steps. They say run OLS, obtain the residuals, which is E. Remember E. Then you say compute D. Most computer programs now do this routinely. So remember, Stata has a command that will give you D. Now, given the sample size, remember your own sample size, given the number of experimental variables, how many access you are using, you can find DU and DL from the appendix of the book. And that basically gives you a test whether the model has autocorrelation or not. But there is one problem. The problem is that he was also only doing this whole assumption based on the idea that ET, sorry, not ET. Let me fix this. So what his idea was that epsilon T is a function of epsilon T minus 1 plus nu T. Remember, this was he was doing. So the idea was this is first order autocorrelation. So in other words, if I do Darwin-Watson test, I'm only testing first order autocorrelation. Not a bad idea, because majority of our data is first order autocorrelated. That's so remember, in economics is not a big one. But in many cases, sometimes it's not first order autocorrelation. That's also a problem. But for majority of the data, it is first order autocorrelation. So remember this. So this table is important to check to understand this table. Then, so the other one is the Bruce-Godfrey test. So remember, the second test is Bruce-Godfrey test. That's very important. And that's a more generalized test than Darwin-Watson. So Darwin-Watson only look at the first order autocorrelation. What is Bruce-Godfrey test? Remember the general test of autocorrelation, which is Bruce-Godfrey test. Same Bruce-Godfrey. Remember previously it was BPG, Bruce, Pagan, and Godfrey, but now it's Bruce and Godfrey. Okay, and their test is very simple. They said, remember this. So their idea was this. This is my model. I was thinking of multiple order autocorrelation. I don't know how many order, up to P. So I'm looking at up to P order autocorrelation. And I'm doing this null hypothesis. All of them are equal to 0, which means there is no autocorrelation. So he said, if I test this against this model, I know whether the model has autocorrelation or not. So very simple logic. So based on this, he created his test run. And he said, run this model. What is this model? This is interesting to know. You have Et, remember my E is there U hat. Okay, this is Et. So run Et on Et minus 1, on Et minus 2, up to Et minus P, up to whatever way you will think about it. But you have to be an economist. You should know what is the relationship. So you do this. Find the R square. Remember, this is my second model. Second model means I run my Y on X. Then I have Y ET on this. This is my second model. And do this test. What does it mean? They said N minus P into R square, this value is distributed as chi-square distribution. So say this is a chi-square distribution. And if you do this chi-square distribution test, so if we go down, we're saying you do this chi-square distribution and you would be able to see whether your null hypothesis is accepted or not. So if it's not accepted, what is your null hypothesis? Your null hypothesis is no autocorrelation. That's your null hypothesis. That's your null hypothesis. If your null hypothesis is no autocorrelation, then if you reject the null hypothesis, remember this is the chi-square test. This is your null hypothesis. So if your chi-square value is here, remember this, and chi-square has a degrees of freedom. So remember, what is your degrees of freedom? N minus P is your degrees of freedom. So based on your degrees of freedom, you check for chi-square value. And if the chi-square value is on this side, you reject the null hypothesis. There is no autocorrelation in my data. So remember that's your second proof of autocorrelation. Okay, which you have to do another home task. So remember, home task are home assignment. These are all home assignment. So then next logical question is, I know that from my data using BPG test or something, I have tested it. How do I solve it? What is my solution? The first solution is, let me start with this first logic. My model was Y equals to alpha plus beta xt plus epsilon t. Remember, I have an autocorrelated model, which is epsilon t is equal to rho epsilon t minus 1. Again, I'm using Darwin-Watson first order autocorrelation plus nu t. Remember, I'm using nu and I'm not saying v. This is v and this is nu. So remember the difference between how to write nu and v. Okay. So that's your first order autocorrelation. So we have this. An idea is that if this is my model, I don't know why I erased it. Let's go back again. And if my model is this, yt is equal to alpha plus beta x t plus epsilon t. So if I say yt minus 1 is equal to alpha plus beta x t minus 1 plus epsilon t minus 1. And if I multiply this with rho, so this will be rho y t minus 1 is equal to rho alpha plus rho beta x t minus 1 plus rho epsilon t minus 1. So remember this one. And then if I subtract these two, this minus this, I will get y t minus rho y t minus 1 equals to alpha into 1 minus rho plus beta into xt minus rho xt minus 1 plus nu t. What is nu t? Because nu t by definition is equals to epsilon t minus rho epsilon t minus 1. And on this side, this minus this is equal to nu t. So then they said, okay, why don't you consider this as a new y star? And this as a new x star? And this as an alpha star. So the new model becomes y star, which is actually a difference. Remember, this is y minus this. Y star plus equals to alpha star plus beta x star plus nu t. And nu t is no longer autocorrelated. So this model is Euler's fine. So that's how I corrected it. So in other words, we're saying that the correction is very simple. Make a difference. If you know the value of rho, you just rework on this data and you know this. So one simple logic of removing autocorrelation is you subtract the previous value, which is known as the first difference. And in this case, I'm assuming rho is equal to 1. You may or may not. You're just saying, look, if you, even the moment you subtract it, if you don't know the value of rho, we'll come back on the value of the rho. If you don't know the value of rho, just subtract it. And this model, which is the difference model, first difference model, this model is not correlated. So in other words, what we're saying that we can remove autocorrelation by simply taking the difference. That's your first order autocorrelation removal method. Okay, so that's what your logic is. There is also another way to say this. This is another method. So this is one way to remove it. Second method of removing it is that I can first find out the rho hat. What is the rho hat? Remember, we already find out D is equal to 2 into 1 minus rho hat. So remember, we have already found out. So if I solve this from here, I can find out rho hat is equal to this. So from here, I can solve this. I said, oh, I know the rho hat because D is known. Darwin has already given us. So if the Darwin has given me D, then rho hat is equal to 1 minus D divided by 2. So that's another way to say, okay, previously I was assuming a rho equal to 1, first difference method. But now I can actually estimate rho. And I can estimate rho as hat as 1 minus D divided by 2. And Darwin is already known. So the idea is that I can actually estimate rho hat. And if I estimate rho hat, I know what is y star. What is y star? Is equal to yt minus rho hat yt minus 1. I don't have to assume rho is equal to 1. I also know what is x star. What is x star? X star equal to xt minus rho hat xt minus 1. So yes, I can solve this. So remember, it is possible to solve this if we do this. So another way to solve autocorrelation is to actually estimate that using rho, find rho from the Darwin's D. Now, Darwin's D is still a good model. Only then it's a model for first order autocorrelation. So there are different methods, but there is one method that I want to come back. Let me see. Let's see where is it. See it here. Okay, it's not here. It's very strange. So there are quite a lot of different methods. There are different methods. There's an iterative method, which is no longer used, so I'm not worried about that one. You see, there is a method. There is also a method where I can actually do an iteration. What is the iteration? I don't know the value because it may not be first order autocorrelation. So in that case, they said, why don't I just subtract different, assume rho equal to different value. But I think the method that I like it is in the appendix. Let me see. Should be somewhere here. Ilrethlu, Telneger, Cochrane, Orcutt. Remember, these are all different methods they're talking about it. But there is a Darwin's D. This is the one. This is the method. So this is Darwin's D method. What he did, he recreated this model. He said, remember my yt minus rho yt minus 1 equals to alpha 1 minus rho plus beta x minus beta into rho. So remember this. So he said, take this one to the right-hand side. That's what he did. And he said, why don't you estimate this model? He said, if you estimate this model has no autocorrelation because this is my new. So this model has no autocorrelation. The only problem is, this is where you see the model is non-linear. So I don't like it, even though it's a solution, some people accept. I don't think it's correct. Why? Because this is a non-linear model. You have to estimate both rho because this is where it is non-linear. So in a non-linear model, using OLS does not work. So remember, this is why Darwin's two-step method, which is also very popular, but is no longer I don't rely it on because it's a non-linear model. So if the model is non-linear, then you should not do the OLS because OLS is based on linear
model.
sequence. Clear? Let's go back to the class. Okay. Everybody got clear idea?